Hello, good morning everyone. मानसी, प्रज्योति, ऋतिक, निकिता, प्राजक्ता, संध्या, रोशन, आकाश, दीपक, हर्षल, अन्नन, उत्कर्ष, किमया, मानसी, आदर्श, प्रक्षेप, सिद्धि, लीना पवार, किरण ताड़े, लवेश, प्रांजलि, हेमांगी, प्रवीण, नेहा, समीक्षा, निशा, अक्षया, वैशाली, प्रणीता, पूजा, दिनेश, दीपेश, प्रांजल, लीना, मीरा, सुप्राप्ति, शिरीन, फरीन, प्रज्ञा, प्रतीक्षा, अथर्व, श्वेतांजलि, राधिका, निशांत, हर्षदा, पूजा आणि नेहा. Okay, I welcome you all. Prachiti, good morning everyone. Am I audible? आवाज आ रही है आप लोग सब लोगों के पर? Am I audible? Naneshwar sir, good morning and welcome. Yes, okay. So today we will have a discussion on the refined and more advanced technology in case of chromatography is HPLC, high performance liquid chromatography, which is synonymously called as a high pressure liquid chromatography. Why there is a changes in name as per the revolution or evolution with respect to the chromatography. Okay, audible, yes, okay. So we will have a discussion over it. Rutuja, good morning. Then what exactly the basis of high performance liquid chromatography, how it is different from other techniques, and why it is so called as the most adaptable and adaptable techniques in case of chromatography. What are the different principles on which this is based. Then we are turning towards the instrumentation part of the HPLC. So let's get started with the high performance liquid chromatography. Good morning, Shweta. So high pressure or performance, initially there was a concern that as we have discussed in case of Van Dimter equation also, that increase in the pressure, now the increase in the rate of mobile phase can increases proportionately up to optimum level your resolution rate. Okay, the resolution by using column can be effectively optimized by using high mobile flow rate. So scientists or the chromatographic revolutionary or evolutionary scientists have come to the conclusion that if we force the mobile phase through the column, then it will definitely increases the chromatographic separation or resolution, and that's why this high pressure means the use of pumping system to pressurize the flow rate through the column can effectively leads to the highest amount of resolution. That is what the basis of this high pressure liquid chromatography. But as such, this high pressure is used when compared to the classic chromatography. When we compare it with the classic chromatographic techniques, the flow of the mobile phase in case of classic chromatography is generally based upon the gravitational forces. As we all know, the what we can call it as a flow of the mobile phase can be proportionately increases or decreases with respect to the gravitational forces. But HPLC is a refined techniques in which you are going to pressurize the mobile phase through the column so that you can get the efficient amount of resolution. Separation of the components from a mixture is achieved by pumping mobile phase at the high pressure using appropriate displacement pumps or the gas pressure. You just have to choose the appropriate amount of displacement pumping system so that you can effectively pressurize the mobile phase through the column with the particle size maybe ranging from 3 to 5 micrometer, or more refined manner it is 2 to 50 micrometer. When we called it as a 2 to 50 micrometer, it should be the small particle size. Akash, Nitish, Nuja, Rakesh, good morning everyone. Okay, so what I mean to say is, when we called it as a high pressure liquid chromatography, historically it is called as a high pressure liquid chromatography, but it is what the limited connotation in case of HPLC. Scientists comes to know that it's not just the high pressure liquid chromatography, but due to the high pressure, the performance of the analysis or the analytical chemistry has been increased multifold, and that's why it should be the limited connotation to use high pressure instead of high performance. And that's why the more refined word in case of HPLC is now high performance liquid chromatography as a replacement to the high pressure liquid chromatography. As you all know, it's a high performance liquid chromatography. Moreover, it is improved performance when compared to the other conventional column chromatographic techniques. No doubt about it, HPLC has made it possible to increase the performance of the chromatographic separation and identification just because of its increased flow rate. And hence the term high pressure is somewhat misnomer, and the term high performance has been replaced with it. Okay, so HPLC is a high performance liquid chromatography now. Okay, so what is HPLC? When we call it as HPLC, it is the most widely used analytical separation techniques. No doubt about it, because whenever you handle this technique at the experimental level, you come to know that HPLC is the most sophisticated, most adaptable and most efficient technique of separation in case of a differing mixture of component system. It utilizes the liquid mobile phase and a packed column. Remember, a packed column of separate components. Remember, the mobile phase is liquid as always because it's a liquid chromatography, but it uses adsorbent material of a packed column inside it for the stationary phase. Okay, and that's why no doubt to say that this HPLC is majorly based upon the principle of adsorption chromatography, because there are active components of the adsorbent on your stationary phase where your components mixture will be get separate out depending upon its adsorptability towards the stationary phase, and this adsorptability is generally differing from one component to another component only because of the differences in the affinity towards the active stationary phases. Okay, so that's what the forms the basis of HPLC. It uses the liquid mobile phase and packed column or the adsorbent silica material in case of column as a stationary phase. Yes, there is a pressure range. Yes, there is a pressure range which ranges from 50 to 300 bar. We will cover it. Okay, we will cover it. 50 to 300 bar will be the optimum pressure application in case of HPLC. Okay, we will have a discussion on it. Okay, it uses the high pressure to push solvent through the column. Remember, we already dealt with it that this system is unique in the case of pushing. Okay, because it uses the high pressure, which I already said that 50 to 300 bar will be the pressure or optimum pressure for efficient separation of your mixture, and that's why this technique is unique, because it uses the high pressure to push the solvent through the column. Why it is popular? Because it is a sensitive technique. When you go through the application pages of the HPLC, you come to know that the technique has been efficiently used for the small differences in the separation of the mixtures, and that's why this technique is popular just because of its highest amount of sensitivity. Okay, ready adaptability. Remember, it is the robust technique. In case if you changes the separation mixture, you can easily change the sensitivity, and that's why it is easy to change it from one solvent system to the another solvent system. Hence, it is readily adaptable and accurate quantitative determination. We will have a discussion on how quantitative estimation or determination helps in the HPLC also. But what is the popularity parameters in case of HPLC is sensitivity. It is the highest sensitive instrument. It is readily adaptable. It is readily adaptable to the different mobile phase systems. Suitability for separating non-volatile species or thermally fragile species. You come to know that the amino acids or the protein separations in case of differing mixtures will result into the separation or thermally instabilization of your amino acids or non-volatile species, and due to which it becomes really sensitive to handle such a amino acid mixtures. For this purpose also HPLC has proved its futility or its application in case of thermally sensitive materials. Okay, yes, Raj, good morning. Ramesh, Nahid, good morning everyone. Why it is popular? Widespread applicability to the substances that are of prime interest to the industry, because it's not just a sensitivity and adaptability, the amount of its linkages with the industry, because industry has no specific structure or rather a specific interest in your sensitivity and adaptability unless it shows the applicability. Remember, it shows the applicability to the industrial application also, because the industrial separation techniques or rather the materials for which the industrial separation requires can be easily adaptable in case of HPLC, and that's why it is widespread applicable in case of industry to many fields of sciences and to the public also. We will have a slide on application also where you come to know that the variety of areas, the variety of domains which will be covered by this technique called as HPLC makes it a very applicable and popular technique. Ideally suited for the separation of and identification of, as we already said, amino acids and proteins, nucleic acids, hydrocarbons, carbohydrates, pharmaceuticals, pesticides, pigments, antibiotics, steroids, and variety of other inorganic substances. It's just an introductory or summarized list of where should be the separation and identification of HPLC helps. It may ranges from amino acids to the proteins, nucleic acid, hydrocarbons, carbohydrates, pharmaceuticals, pesticides, pigments and antibiotics, steroids, and various other organic and inorganic materials. Jagruti, good morning. Now, what is the history behind it? Now, initially the liquid chromatography with the help of a glass column has gained the importance. Remember, the liquid chromatography, it's not the novel technique right now. It has been used past so many years, and that's why liquid chromatography earlier uses the glass column. Okay, but what are the specifications in case of glass column? Is its diameter, which is 1 to 5 centimeter higher, length of the column 50 to 500 centimeter higher, size of the solid stationary phases which we are using for the packing material in case of glass column is its diameter is 150 to 200 micrometer. Remember, if there is a diameter which is 150 to 200 micrometer, considering the average particle size, now in case of HPLC it is 5 to 50. Okay, 5 to 50 or more specific 2 to 50 micrometer. It's very less in case of HPLC as compared to the earlier techniques. Okay, so this 2 to 50 micrometer as compared to 150 to 200 micrometer results in the flow rate optimization or rapid flow rate through the column. Earlier, the liquid chromatography, which uses the higher amount of length of the liquid column, its diameter is also high, its solid particles diameter is also more, that results into flow rate of the mobile phase low and separation requires a much more time. Remember, it's not just a matter of flowing through the column, but the time required for the separation is also high in case of liquid chromatography or normal phase liquid chromatography. decreased particle size of the packing causes increase in the column efficiency. Remember, as you decreases the size of the packing column or adsorbent material, you increases its surface area. Remember, as we all have been dealt with the physical pharmacy, why we will have optimum or decreased level of particle size, because the decreased level of particle size increases the surface area of interaction with the surrounding medium, and as soon as the surface area increases, the resolution and efficiency of the column also increases. The diameters in case of this for the solid adsorbent material is 3 to 10 micrometer for better resolution, but the optimum parameters or optimum diameter in case of this adsorbent material is 2 to 50 micrometer, as I already said in case of HPLC. Okay, HPLC utilizes 2 to 50 micrometer range of particle size so that you can get the efficient amount of efficiency in the column separation. Snehal Patil, Yadav Priyanka, good morning. So this technology requires sophisticated instrument, no doubt about it, because it is dealing with a variety of the samples, and also delicacy of the instrument will result into a sophistication instrument fabrication, and that's why this method HPLC has been devised based upon these two parameters, that is using the forceful introduction of your mobile phase inside the column and decreasing the particle size of the column will definitely results into the better resolution or increased column efficiency. Okay, what are the advantages with respect to the HPLC? Higher resolution and the speed of analysis, no doubt about it. Higher resolution just because of increased mobile phase rate, and speed of analysis just because of decreased particle size will result into higher resolution and speed of analysis. Greater reproducibility due to close control of the parameters affecting the efficiency of a separation. This technique allows you to have a proper amount of control over the various parameters like the flow rate. You can easily determine and optimize and even control the flow rate of the mobile phase, and that's why it results into a greater reproducibility. Easy automation, that instrument in case of HPLC is the highest amount of fabricated instruments, and that's why it results into the easy automation of the instrument operation and data analysis. Adaptability to the large scale and preparative procedures. This technique is not only adaptable in case of analytical chromatography. Remember, analytical chromatography, where the prime motto of any chromatographic technique is what? The identification. But this HPLC technique can be easily scaled to the large scale production and can be easily adaptable for the preparative chromatographic techniques also. Okay, so these are some of the advantages. Advantages continues just because of the two major advantages: stationary supports with very small particle size and large surface area, that gives rise to the advantages to the HPLC, and appliance of high pressure to the solvent flow, that also gives rise to the advantages to the HPLC in case of what we can say identification and preparative chromatography. I hope you know the basic idea behind the HPLC. Just remember the two different points, that stationary support in case of this will have a very small particle size, and this results into the higher enactment or what you can say interaction between the stationary solid phase and your mobile phase along with the solid mixture. Along with this, the appliance of high pressure will result into increased mobile phase rate. Okay, what are the application part of this stationary HPLC? So HPLC has been used for manufacturing. First application is what? The manufacturing. During the production process of pharmaceuticals and biological products, no need to discuss. Legal application is second one. Remember, it's not just for the pharmaceutical production purposes. Legal applications are there: detecting performance enhancement drugs in the urine. Remember, there are so called as a doping test doping tests are there. You must have heard that the sports athletes were tested by WADA, World Anti-Doping Agency. It's not our WADA, it's World Anti-Doping Agency, which tests the your athletes for its performance enhancement drug consumption, and for this purpose it uses HPLC for separation of your urine components from the performance enhancement drug components. Third one is the research. No doubt we will have to deal with the HPLC when you will dealing with the research development techniques like separation of the components of complex biological samples or of similar synthetic chemicals from each other. Fourth one is the medical application. It has been utilized for detection of vitamin D levels in the blood serum. That are some of the major domains in which the application of HPLC can be useful. I can summarize it in the form of Ojal Jadhav, good morning. Manufacturing, legal aspects, research and development, and medical applications are some of the applications of your HPLC techniques. There are two important concepts with respect to the chromatography which we have left, is the capacity factor and the selectivity factor. Now remember, capacity and selectivity factors is determine or rather gives you the specifications or your stationary phase capability to deal with the varied amount of mixtures. Remember, it is the capacity of your mixture to get attached or adhere to the stationary phase, and it is important to understand the column resolution. That's why this capacity factor and selectivity coefficient are important to study. Okay, so first is the capacity factor. Capacity, remember these equations because there are questions with respect to your numericals based upon the chromatography. We will have a lecture on it. Okay, K dash is the capacity factor, which is the ratio of amount of time analyte spends in the stationary phase to the amount of time it spends in the mobile phase. Remember, the capacity factor is the amount of time the analyte means a mixtures component, analyte spends into the stationary phase. Stationary phase time is what? The retention time minus the introduction of sample or non-retention time. To the non-retention time is your mobile phase retention time. The mobile phase, the time required by the analyte to get inculcate into the mobile phase. Remember, when in simple terms, when I called it, the capacity factors is the ratio of your analyte's retention time by stationary phase and the amount of time it spends in the mobile phase. It's what the capacity factor. Now, selectivity coefficient is the ratio of two capacity factors for two different peaks. Okay, suppose there are two components A and B to be get separated, and you will get the different peaks on your detector signals or the chromatogram for specific analyte, that is A and B. Okay, now if who is get first eluted, if I say this is the chromatogram, if this is the chromatogram, let me chart in the comment box. Okay, who is get first eluted out, कौन सबसे पहले इल्यूट होगा, A और B? Who will get separate out first? Is it A or is it B? Siddhi says B. Radhika also says B. Okay. Remember, the elution of an analyte is proportional to the time. We will have to look after to the time. Okay. So this, if this first peak is there for the A, okay, ये पहला पीक A का है, दूसरा पीक B का है. अब यहाँ पे इस एक्सिस पे क्या बता रहा है आपको कि टाइम कैसे बढ़ा है और उसके हिसाब से एनालाइट कैसे रिजॉल्व होते हुए सेपरेट आउट हुए हैं. कंसिडर दिस एज अ सी. ओके, 3 एनालाइट थे आपके मिक्सचर में, ए, बी एंड सी. ओके, सो उसमें से ए जो है, ए ने आपको पहले सिग्नल दिया है. रिमेंबर, ए ने आपको पहले सिग्नल दिया है. इसका मतलब यह होता है कि ए सबसे पहले इल्यूट होगा. Remember, you all have mentioned B. There is some conceptual miscalculation by your mind that B is not the one. It's A. It's A which is eluted first and then comes the B. समझ में आ रहा है आप लोगों को? ये टाइम जो एक्सिस है आपका, ये बता रहा है आपको कि जैसे जैसे टाइम आगे बढ़ा है वैसे वैसे कंपोनेंट्स आपके सेपरेट आउट होने लगे हैं. बट मेरा क्वेश्चन ये था कि पहले कौन एल्यूट हो रहा है या पहले कौन बाहर आ रहा है या सेपरेट हो रहा है, तो वो है ए. ए इज गेट सेपरेट आउट फर्स्ट एंड देन इज द बी एंड देन इज सी. ओके, आई होप यू क्लियर विथ इट. यस प्रवीण, good. It's A first. Okay, now why it is important to understand who is getting first eluted out. Okay, so जब हम लोगों ने कैपेसिटी फैक्टर देखा तो हमें देखना पड़ेगा अभी सिलेक्टिविटी फैक्टर. सिलेक्टिविटी फैक्टर इज द रेशियो ऑफ कैपेसिटी फैक्टर फॉर द पीक विच इज eluted later than the peak to which is eluted earlier. Okay, remember, I am going to repeat it again. Okay, yes Radhika. Okay, so what is the selectivity factor? Selectivity factor is the ratio of capacity factor of an analyte which is eluted later. Which is eluted later is what? B. Means the capacity factor for B is what? KB. Okay, because it is eluted later to the capacity factor which is eluted earlier, which is Ka. Okay, okay, now you know that the retention time for the B, retention time for the B is TR2. Okay, retention time for the B is TR2 minus T0 is what? Non-retention time is over here where the sample has been introduced in the mobile phase. Okay, now in case of K dash A or Ka, that is capacity factor for A is TR1 minus T0. TR1 is what? The retention factor for your A sample or A component or a first peak. And if you calculate the ratio of TR2 to the TR1, I hope I will have to clear it again. Okay, so remember, when I say it's x-axis which denotes the time and y-axis which denotes the signal, you are getting the detector signals, and as the time increases you will get the refine or a more amount of components into your chromatogram. When I say A, it is eluted out first. As soon as you introduce the sample, you will get the first peak of A. That means A eluted first. Okay, next is B, and then if you have another component, then it is C, and on that basis you can calculate the capacity factor and selectivity factor. Capacity factor is what? The retention time of your peak to the non-retention time, that is introduction of the sample, to the T0, that is non-introduction of the sample or non-retention time. Okay, that's how you will get the K dash for individual peak, maybe A, maybe B. Okay, and if you just divide the K2 or what the selectivity, if you want to calculate the selectivity factor, if you calculate the capacity factor for B and if you divide it with the earlier eluted sample, that is capacity factor for A, you will get the alpha, that is selectivity factor. I hope it is clear now. If you make the ratio or if you calculate the ratio of peak which is eluted later to the peak which is eluted earlier, you will get the selectivity factor, that is alpha. Now what is capacity factor? We already dealt with it. Okay, if the substance is not related by the stationary phase, its capacity factor K dash will be 0. Okay, because if the substance has not shown any affinity or adsorptivity towards the stationary phase. Okay, remember what is capacity factor is what the amount of your solute or analytes affinity towards the stationary phase. What capacity factor denotes as the amount of solutes get attached or adhere to the stationary phase, and if K dash is 0, that means the amount of substance is not retained by the stationary phase. It should not show or it has not shown any sort of affinity towards the stationary phase. That's what K dash is equal to 0. Okay, Siddhi, it's no issue. That's what the prime job of me to get clear with respect to all the parameters and all the concepts of chromatography. Okay, so if K dash is 0, that means your substance is not retained by the stationary phase. It is clear. Small K dash, that means if your K dash is less than 1. When I say a small K dash, if your K dash that is capacity factor is less than 1, values show that the components are only retained slightly by the separation column. When I say the small value of K dash, it means that the K dash value is small. It is representative of the concept that your sample has been retained slightly only by the separation column or by more specifically stationary phase. Their peaks are located close to the non-retained peak. Remember, if the K dash is 0, that means if you get the chromatogram like this, and as we all know, the non-retained peak, or we call it as a non-retention peak, that is the TR0 is over here, and if your K dash value is less than 1, you will get the peak exactly just aligning outside of your non-retention peak, and that's why the separation cannot be labeled as efficient separation. Okay, so what should be the optimum capacity factor? Optimum capacity separation range for K dash is between 1 to 15. Remember, optimum separation will be possible if you get K dash value in between 1 to 15. Values for greater than 5 mean long retention time with associated band broadening. In that case also, if you get 1 to 5, it is what the optimum range, highest amount of optimum range for K dash, that is capacity factor. And if the K dash has been extended from 5 to 20, remember 5 to 20, it shows that, or it is synonymous to the factor that your sample components has been retained for a longer period of time in the stationary phase. But as we all know, there is a disadvantage with respect to the longer amount of adsorptibility or retention on the stationary phase. It results into the band broadening, which is also a concern in case of chromatography. That's why 1 to 5 is what the optimum amount of capacity factor range you will get for a highest amount of resolution. Okay, so that's what I hope. Capacity and selectivity factor along with their equation. Remember, you need to understand the equation also. There has been a question in case of your exams for these capacity factor and selectivity factor also. Along with this is also important in case of GPAT because it is a conceptual part. Okay, so why K dash is equal to 0, what should be the implication? If K dash is less than 1, what should be the implication, and what should be the optimum range of K dash to get a narrow amount of peak. Now there are variations in case of HPLC. HPLC has been a varied amount of separation or a varied amount of its what we can say dimensions. The liquid chromatography mode has been defined, or I can call it as the types of liquid chromatography. Okay, normal phase chromatography, reverse phase chromatography, size exclusion chromatography, ion exchange chromatography, affinity chromatography. We will have to deal with individual components, more specifically size, ion and affinity chromatography in details in our remaining session. But as we have already dealt with the normal phase chromatography, reverse phase chromatography, what is the difference? Let me know in the chat box what is the difference between normal phase chromatography and reverse phase chromatography. Do it fast. Okay, I'm going ahead. In short, if you have this table, you can get the instrumental idea regarding what is HPLC's variations. A normal phase chromatography packing material is silica gel, and in case of reverse phase it is silica C18. In case of size exclusion it is porous polymer. Ion exchange gel packing with the ligand. Mobile phase, I hope this is what the basis of your separation. Mobile phase, normal phase, reverse phase. N-hexane will be the normal phase. Methanol water in case of reverse phase. THF, tetrahydrofuran, is what the size exclusion mobile